Hello everyone, this is tutorial 11 and today we are going to discuss Laurent's expansion of complex variable functions. So let's start out with some revision. You used to know so-called Maclaurin's expansion. Let's start with Maclaurin expansion. What it was? Let me remind you. So some function f of z could be expanded into the series of such expressions. So f of 0 plus f prime of 0 divided by 1 factorial z. I'm using the letter z, even though it's more typical for complex variable theory to use the letter z, but I just, decided to do it from the very beginning. In the past, when you didn't know anything about complex variable theory, you mostly used letter x, but it doesn't matter. Okay. So f prime prime, the second derivative, 0 divided by 2 factorial z square. And let us write out one more term, and this should be enough. So you probably immediately recalled this Taylor expansion. So you know what? Actually, to build to obtain the Taylor expansion, you need to just calculate these derivatives and their value at point z is equal to 0, and then to substitute to this expression, and that's it. By the way, from your tutorial sheet, this is question 2. This is question 2. So you are asked to calculate directly the first two terms, or the first two powers of the Maclaurin's expansion for the given function. So I think it's a pretty easy task for you. But you know what? Let's just not pay too much attention at these coefficients. These are actually numbers. Let's denote them as C0, and this coefficient, let's denote it by C1 z plus C2 z squared, and so on. I'm doing this not to be distracted too much by these big expressions. So Maclaurin's expansions looks like, the infinite sum of terms. Each terms is some power of z, to the power of 0, z to the power of 1, z to the power of 2, with some coefficients. And you know how to calculate these coefficients. I just decided not to go into details. You know what? This expansion has different names, actually. Sometimes mathematicians say that this is expansion about a point z is equal to 0. So they use this term. Another way, sometimes they build this phrase in a different ways. So this is expansion again, expansion in powers of z, which seems to make more sense. So actually, this expansion has actually three names. The first name is Maclaurin's expansion. Everyone immediately will know what you are asking for. If you need Maclaurin's expansion, it means that unit expansion about z is equal to 0, and at the same time, some other people can call it expansion in powers of z. Personally, I like the last phrase because it conveys the meaning best of all. Okay, so but then you found out there is a generalization of Maclaurin's expansion, which is called Taylor's expansion. Taylor's expansion. So Taylor's expansion looks pretty similar, but the difference is that let's look at this form. Because I don't want to go into details as to how these coefficients look like. We don't care about them at the moment. So what is Taylor expansion? The difference between Maclaurin's expansion and Taylor expansion, that is not in powers of z, it's in powers of z minus 0. Let's write it down. So the first term will be the same. Then you'll get C1 times z minus z0 in the first power, plus C2 z minus z0 in the second power, and so on. Let's write down the third term as well, and so on until infinity. So this is the difference between Taylor's expansion. So you can immediately, looking at these two formulas, two expansions, you can immediately come to conclusion that Maclaurin's expansion is just a special case of the more general Taylor's expansion, when this Z0 is equal to zero. Yeah, Z0 is equal to 0. And by the way, coefficients, of course, you have a different formula for coefficients. Here, you needed f prime of 0, but in this case, you will need f prime of, for example, C1. Let's write down here, prime 1. F prime, it won't be at point 0, it will be in point 0, Z0, sorry, Z0, and so on. C2 will be f2 primes of Z0 divided by 2 factorial, and so on. And so, of course, as well as Maclaurin's expansion, this expansion has different names. So one name is it is expansion about point z is equal to z0. This is the first name. This is the first name. Sorry, it's writing out of view. And the second name is expansion in powers of not z like in the previous case, but z minus 0. Z minus 0. So you should be familiar with both of these names. Okay, but now this was a revision of the previous material from the previous semester, from the past, in other words. But what about this semester? We are discussing complex variable functions. Can they also be expanded into Maclaurin's or Taylor's expansion? And Dan says yes, but you know what? Just like with everything else in complex theory, we have a sort of generalization of this Taylor expansion, and it's going to be called Lorentz. I don't know how to pronounce it. Lorentz expansion. This is generalization of Taylor's expansion. Just like everything else, many mathematical concepts get generalized here in complex variable theory. So let me write down how the Lorentz expansion looks like. So I'm starting with the same. Terms like in the Taylor's expansion. I'm just copying them from here. So C1 z minus z0 plus C2 z minus 0 squared plus C3 z minus 0 z0 cubed and plus so on. But this is not the end of the story. So far, I haven't written anything new to you. It looks just like Taylor's expansion, but what's interesting, there can be more and more terms here. C minus 1 divided by z minus z0. Nothing like this happened before in Taylor's series. In Taylor's expansion, you are just not allowed to use negative powers of this z minus z0. But here it's quite common. Plus c minus 1 z minus z0 squared, and so on, and so on, and so on. So this looks like a real generalization of the concept of Taylor series. And moreover, you can see that again, this Taylor series corresponds to these first terms. Not first terms, there could be infinite number of these terms. But this part corresponds to a Taylor series. And there can be this part, and this part is so important here in complex number theory that it was even given a separate name, a special name. This is the principal part of Lorentz expansion. So it's super important. And why, you will know, you will find out about it in our next tutorial, tutorial 12, which is the last in this semester. But now we are supposed to talk only about Lorentz expansion. And so it turns out that we need to learn how to do this Lorentz expansion. You know, many tricks which you used in the past to expand your functions into Taylor series can be used here as well. But maybe you forgot about all these tricks. That is why my task is to remind you. So the first approach, of course, is to just calculate, to calculate these coefficients C1, C2, and so on by this formula. By the way, the formula is actually the same. Formula is actually the same. And then to substitute them. But no one ever does this. This is quite a long story. They only give you one question, question number 2 in this tutorial sheet, just for revision, just to for you to see the whole picture. But no one ever fancies doing expansion in this way because it's so long, so such time consuming and very boring. An alternative approach is to to use some so-called canonical expansions. And now we need to write them all down. Unfortunately, it takes some time, but we simply can't do without them. So, canonical expansions, canonical expansions, canonical expansions. So these canonical expansions play the role like a list of the most popular functions and whose expansions you should know by heart, or at least to have a good cheat sheet in your exam, of course. It could be likened like the list of derivatives. To be able to differentiate functions effectively, you are supposed to know some basic derivatives, the list of basic functions. And here the situation is the same. Canonical expansions form the basis of our further, more difficult task. Okay, I'm talking too much. It's time to start writing. Okay, the first function is 1 divided by 1 plus z, the simplest function probably. This expansion looks like this: 1 minus z plus z squared minus z cubed plus so on and so on. And to the right, we need to write so-called region of convergence, because it means that you are allowed to use this expansion only when you are absolutely sure that your z, absolute value of the z, is less than 1. Only in this case, this series will converge. Otherwise, you are just not allowed. This formula simply doesn't work. Okay, the next function is 1 divided by 1 minus z. Actually, this function could be obtained from this one by substituting z with minus z. But you know what? It's so beautiful that I just can't help writing it to you. This is the most beautiful expansion ever. Look at this, super simple. And the region of convergence is the same. It's the same. So it's good news. Okay, what is the next function? The next function doesn't look very beautiful, but what can you do? It's a generalization, actually. This is general formula. So you can immediately see that the first formula could be obtained from this one when n is equal to minus 1. But what is general formula? We should know the general one. So I'm writing it to you. 1 plus nz plus n minus 1 divided by 2 factorial z squared plus n times n minus 1 times n minus 2 divided by 3 factorial z cubed, plus so on and so on and so on. Many, terms there. And again, the region of convergence is the same. It has been the same so far. Okay, open the what next one. Next one we have logarithm. Logarithm of the same expression, 1 plus z. It will be z minus z squared divided by 2 plus z cubed divided by 3 minus z to the power 4 divided by 4, and plus so on. Maybe that's enough for you to see the pattern. Look at this. It's not factorials. It's just numbers 2, 3, 4. I'm not making any mistakes. It's just not factorial. And the region of convergence is the same. Okay, let's move to number 5. Number 5 is super famous exponent. Exponent has this extension: 1 plus z squared divided by 2 factorial by z cubed divided by 3 factorial plus z to the power 4 plus 4 factorial plus so on. And the region is convergence is the whole complex plane. It could be used for any z, no limitations. No limitations at all. Well, this is quite good news. Okay, but it's not, it's only half of the list, unfortunately. So let's move to number 6 now. Number 6 is sinus z. Sinus z has a very beautiful expansion. Z minus z cubed divided by 3 factorial by z to the power 5 divided by 5 factorials, and so on. You can see the pattern. if you need to, you can usually write the next term and the next and this next one. You can easily guess what the next term is going to be. So it means that you see the pattern. And again, the region conversion is the whole complex plane. You can use it for any z. It will always converge. And you know what? Just next to sinus that, I want to write you this hyperbolic sinus, which is denoted like this, if I'm not mistaken. Hyperbolic sinus. It's a very interesting function, even though it has nothing to do to trigonometry, but nevertheless its behavior is amazingly similar to the behavior of trigonometric sinus. So look at this expansion. Indeed, it looks pretty similar. There are some differences, of course, but as you can see, the only difference is that all the terms are positive, unlike here when the signs are alternating. This is a striking, amazing similarity between this function. Okay, now we need to move to cosinus of z. And one characteristic of sinus z, look at this. It has only odd powers of z to the power of 1, 3, 5, the next one will be 7, 9, and so on. So sinus always has only odd powers, as opposed to cosine, which has only even powers. Look at this. So here I'm writing only even powers, and so on. Maybe one more term. So on. And again, the last one, I think it's going to be the last one. Yeah, this is the last one. It will be hyperbolic cosine of z. Again, as you may already have guessed, I will have all the positive terms here only. So, and all these expansions, all these formulas are true for any z. So our conclusion is that it's only the first two functions which can be actually the first two formulas which should be used with care, because they have this limitation in the form of a region of convergence. Only under this constraint you are allowed to use these formulas. Otherwise, they simply don't work. They are simply not true. Okay, so this is our basis. Our basis, we are supposed to know, or at least to have at hand, all these canonical expansions. But this is not the end of the story, it's only the beginning. So how exactly should we do these expansions? And how does the assignment sound, by the way, which is really interesting. So let's start with the first example. It's not from your tutorial sheet. This is an example of my own invention. So usually they ask you to do quite a strange thing. They build their phrase something like this: find all expansions. Look at this, sounds already very strange. Find all expansions of our function f of z in powers of z. In powers of z. Okay, you might say that you are pretty familiar with this phrase, in powers of z. We already discussed it in the very beginning of this video. But what does this phrase mean? Find all expansions. What does it mean? Do they mean that the expansion is not unique? And the answer, the sad thing is that yes, no, it's not unique. Before, when you learned calculus and when you studied how to expand your functions into Taylor series, you always got only one expansion. It was just unique. There was even theorem saying that these expansions can be unique only. But here in complex number theory, almost all our rules are broken, and as well as this one. It turns out that sometimes, and more often than not, function can have more than one expansion. Sometimes it can be two, sometimes three, and so on. But how to determine how many expansions you need and how to do this expansion? This is very interesting issue. First of all, you know what? You need to find the point of singularity. So point of singularity. Singularity. What is this guy? Oh, sorry, for my handwriting. Point of singularity. This is the point where your domain of your function is broken, where the function doesn't make sense. Of course, you can't, you are not allowed to divide by 0. By the way, you are not divided by 0 even here in complex number theory. Even though so many strange things cease to be incorrect here in complex number theory, like the square root of -1. It's not considered to be a nonsense anymore. It's quite a, quite a true thing here. But even in this field of complex number of mathematics, it's still not allowed to divide by 0. So it turns out that z is equal to -3 is our point of singularity, because you can't divide by 0. And this point of singularity actually will show you how many expansions you need to expect. You need to plot this number. This is a complex number -3. It's somewhere here. Oh, it's not actually complex. It's a real number. But you know that real numbers now are viewed as a special case of complex number. So it should be depicted here. And then after you plotted this singularity point on your complex plane, you need to draw a circle going through this point, and with the center in that we are going to have two expansions of our function. So this is a trick as to how to determine from the very beginning how many expansions for your function you need to expect. Okay, but now the question arises, how exactly should we do this expansion? Of course, we have a list of canonical expansions, and of course we realize that maybe we should use the first one, which is quite true. But how on earth can we obtain two expansions? Okay, let me first start by copying this canonical expansion here to this first page. So we are definitely going to use this function because our function is pretty similar to this. So let me copy it here. So this expansion looks like 1 minus z plus z squared minus z cubed, and so on. And the crucial thing is that it has this region of convergence. So I'm going even to put a frame around this text. So it's super important. So this is our canonical expansion. Sorry, my paper is sliding out of view. So now we can begin. So it turns out that we should watch out for this limitation all the time. So let's start. Let's start writing by first region. So now let's imagine that we are inside this circle. We are in the first region. This region could be written as absolute value of z is less than 1. That's how you write the region which corresponds to the interior of the circle. So absolute value of z is just less than 1. It means that we are announcing that we are inside the first region now. Okay, so let's write our function. F of z is equal to 1 divided by z plus 3. And let's try to figure out now how can we use this expansion, this standard canonical expansion, to expand our function. It turns out that you need this one in the first place, this one. How can we provide one here? How can we get one here? You know what? The trick is very simple one. You can just factor out 3 out of these two terms in the denominator. You will get 1 plus z divided by 3. I changed the order of the terms here just for the convenience. So if you don't believe me, for example, or if you don't believe yourself, you can always check your result by multiplying this expression again. So 3 times 1 will be 3, and 3 times this guy will be z. So it's absolutely true. And so you can factor out 1 over 3 actually, for the beauty. And now we realize that this expression looks just like this one, like this canonical one. The only difference, when we start using this canonical expression, we are going to substitute z divided by 3, z over 3, wherever we see z here, and that's it. So let's do it. I need more space on my screen. So 1 over 3 will be just, outside, And so let's start. Our first term is 1. We're just copying it. The next term is z. But instead of z, we need to substitute z over 3. Here we have term z squared, but we promised to ourselves to substitute z over 3 instead of z squared, and so on. Let's try. Let's write one more term, and this should be enough. Plus, and so on. So this is our first expansion. And I'm tempted to simplify it a little bit because it's not proper to leave. It's not good, good style. It's not good manners even in mathematics to leave expressions unsimplified. So let's do multiplication and apply some properties of the powers. It will be 1 over 3. The next term will be z, but I prefer not to write 9 here. It's better to write 3 squared to remain to see this pattern. Z squared divided by 3 cubed minus z cubed divided by 3 to the power 4 plus so on. So you might ask me, what was so special about what I've just done? What's the difference compared to what you did in the previous semesters of mathematics? You know what? The fact that z was less than 1 was actually crucial. I just didn't mention it to you, not to distract you too much. But now it's time to discuss it. It turns out that we are allowed to use this canonical expansion only when this condition holds. And we still haven't checked this condition, by the way. So in our situation, we used this expression z divided by 3. Is it less than 1? Is it less than 1? Yeah. I made a mistake. I realized that I made a mistake. Okay, that's good. So it turns out that I didn't write this region properly. It has a radius of 3. Sorry, radius of 3. Radius 3. So the interior of the circle should be written like absolute value of z is less than its radius. Sorry for this mistake, but maybe it's for the better. It's very useful to make mistakes from time to time. It draws your attention to these very special things. Okay, so in our case, let's get back to this z over 3. So we used our z over 3 instead of z in this expansion. But this expansion says, this rule says that your term should be less than 1. Is it less than 1? Of course, yes, because z is less than 3. We are in the region where z is less than 3. That is why if z is less than 3, the whole fraction is less than 1, because 3 divided by 3 is 1, of course. So all we've done just now was absolutely justified. It was absolutely correct. But you might say that it was nothing interesting, nothing new for you. Okay, but let's move to the next region. Next region is the exterior of our circle, and it should be written as z is bigger than 3, bigger than the radius. You describe the whole area outside the circle by this inequality. Okay, what is the difference? Can we use the same expansion, the same trick? And it turns out, no, this time it's not, because this fraction, which you are intended to use instead of z, is not less than 1 anymore. It doesn't satisfy this limitation. It will be, on the contrary, it will be bigger than 1. So it's absolutely outrageous. You can't use this expansion. It's just simply not true. But what can we do instead? Okay, let me rewrite this function here. So our function is here. Last time, our main problem was to obtain 1, so that our function would look just like this canonical expansion. But last time we achieved this by factoring out 3. This time we can't do this. This will be repetition of the previous step, and we already discussed it. You know what? The trick is very simple one. It's laughably simple. We should just factor out z instead of 3, which sounds very weird, but what can you do? It will be 1 plus 3 divided by z. Very strange, very unusual, but that's how all the complex theory is. It's very mind-blowing in some places. Let me check. Maybe I made some careless mistakes. So if I multiply it again, it will be z times 1 will be z, the first term here. And z times this guy, it will be 3. Okay, everything's correct. So just like in the previous case, I can factor out 1 divided by z, not to be too distracted. And we can discuss this function, this expression. Look at this. It looks pretty much like our canonical expression, and the role and this fraction 3 divided by z plays the role of z, which we are going to use here in canonical expression. Is it, but the question is urgent, is it allowed to use our expansion? Is our z is less than 1? And you know what? Look at this, look at your fraction and look at this inequality. If you substitute z bigger than 1, it will be denominator. The whole fraction will be, on the contrary, less than 1. So that's what we're craving for. So the answer is yes. Our function looks properly to be used for expansion. And now we take this expansion, canonical expansion, and wherever we see z, we substitute this strange guy 3 divided by z plus 3 divided by z squared minus 3 divided by z cubed plus so on. Okay, and again, just like last time, I told you before that it's not good manners to leave expressions not simplified. So 3 divided by z squared plus 3 squared divided by z cubed minus 3 cubed divided by z to the 4 and so on. So that's it. So that's how you can obtain different expansions of the same function, and there's nothing miraculous about it, because everything was so logical. I hope you followed my reasoning, so nothing amazing. And moreover, do you remember that in the very beginning of this session I told you about the principal part of Laurent series? So it's not this. So both of these expansions are called actual Laurent series. This function has two Laurent series. But you know what? In the first case, our Laurent series contained only terms with positive power of z, z to the power of 1, z to the power of 2, and so on. There was no negative powers. So the principal part in this Laurent series was missing. It's not necessarily that both parts are present in the same Laurent series. Whereas in this expansion, which was for the external area of external side of the circle, on the contrary, you can see only negative powers of z. So the whole Laurent series consists of negative of principal part only. So sometimes there can be both of them present. Okay, so this was our very first example, and now we need to discuss even more things. Paper. Sorry, paper. So this was expansion in power z, but sometimes you might be asked to find expansion in some other powers. How should it be done? Let's analyze. Let's go over some one more example, which is actually the same function. So it's going to be example number 2. The same. Let's take the same function. It will be more interesting to see things in the same function. And the assignment is almost the same. Again, they ask you to find all expansions, not one, but all expansions of this function f of z, but in powers of z plus 2. You can see the difference immediately. What is the approach to this task? What should you do with this z plus 2? You know what? The solution is very simple. Just denote this z plus 2 by some other letter, t. Then, after that, we can rewrite this whole function in terms of t. And thus, our task will be reduced to the previous one, to the very familiar task. But to do that, we need to do it very accurately, carefully. So, let me express z in terms of t from this idea. And then after that, I should be able to rewrite my function in terms of z. All I need to do, I just need to substitute t minus 2 instead of z here. T minus 2 plus 3. So it will be equal to t plus 1 or 1 plus t. So let me write it. F of t is equal to 1 divided 1 plus t. And we need to substitute it to expand it in powers of what? In powers of z. So, powers of t, sorry. So our task sounds just like the previous task, nothing new. We just did this substitution. This means that we are going to do the same two steps now, the same, things. But at the very end of the task, we shouldn't forget about, getting back to our old variable z. This is the only difference. Okay, let's do this task, and it will be good opportunity to practice our skills again. So the very first step should be to determine how many expansions are there at all for this function. You need to find the point of singularity. In our case, it's t minus 1. Then you need to take a complex plane and plot your point of singularity. This will be minus 1. And after that, you need to plot a circle going through this point of singularity. And the center of the circle should be in the center of coordinate system. And so again, just like in the previous case, we see that we are going to obtain two expansions inside the circle and outside the circle. Okay, let's start with the interior of the circle. Interior of the circle should be written as inequality z, absolute value of z is less than 1. This time it's 1 indeed, unlike the previous time when I did a mistake. Do you remember? We had a circle of radius 3 and I wrote 1 here by mistake, but in this case it's actually correct. Okay, so we are lucky with this example because it's already, we don't need to simplify our function, because it's already canonical expansion. We just need to rewrite it from our list of canonical expansion. This is it. And moreover, we already know that it's allowed to use X expansion because we are, Z. I made a mistake anyway. This time it's a different thing. It's not Z, it's T, a new letter T, because it's all about T here, sorry. Okay, and moreover, we are allowed to use this formula because it does satisfy this limitation. T is indeed equals to 1. And so the only difference is that once you are finished with your expansion, you need to do this inverse substitution. Instead of wherever you see T, you need to substitute Z plus 2. So let's do it. Instead of T, I'm substituting Z plus 2 here. This guy will be Z plus 2 squared. This will be Z plus 2 cubed, and so on and so on. So indeed, we did obtain the expansion, which could be called in terms of, or in powers of Z plus 2. In powers of Z plus 2. Okay, similarly, we are moving to the next region, which is in its exterior of our circle, which could be written as T bigger than 1. By the way, we need to make this inverse substitution everywhere. We can write here, we can rewrite this inequality in terms of z as well. So instead of t, I'm substituting z plus 2 here. Plus 2 is equal to 1. So when you are given the answer, you give it in this way. So my expansion looks like this in this region, and the next expansion looks like this in this region. That is why it's better to prepare them from the very beginning. So let me rewrite it in terms of z as well. Okay, bigger than 1. Okay, so I'm copying my function here. F of t is equal to 1 divided 1 plus t. But now we realize that we are not allowed to use this canonical formula because our t is in this region. So it means that this term is bigger than 1. And this is the case when we are not allowed to use this expansion. But you already learned this trick from the previous example, that to provide 1, you can do it in a different way. You can pull out t, and then you will get 1 plus 1 divided by t. So let me pull out 1 divided by t here. And so our function is here. And this term does satisfy this limitation. Because when t is bigger than 1, it means the denominator is bigger than 1. But the whole fraction will be, on the contrary, less than 1. So it means that it does satisfy uh, our condition. Okay. So now we need to look at this canonical expansion and substitute 1 divided by t instead of t everywhere. So 1, how did it go, this canonical expansion? It was 1 minus t, but we put, instead of t, we put everywhere 1 minus 1 divided by t. Then it was plus 1 plus t squared, but we put 1 divided by t squared, and so on. Let me write down one more term, and so on. Now we need to simplify this expression a little bit. 1 divided by t minus 1 divided by t squared plus 1 divided by t cubed minus 1 divided by t to the power 4, and that's enough. And again, um, we need to recall that it was all about z, not about t. T was the variable of our own invention. So instead of t, we need to make this substitution. We need to write z plus 2. So z plus 2 squared plus 1 divided by z plus 2 cubed, and so on. I'm even lazy to write the next term. So just like in the previous case, we have two different expansions corresponding to two different areas. So the purpose of this second example was to show you how to cope with this situation when you are asked to find expansion not in powers of z, but in powers of something else like z plus 2, z minus 3, and so on and so on. The best approach is to make this substitution, the simplest one. Okay, so let's move further on. The next example will be it will be more difficult, but interesting at the same time. So let's move to example number 3. Example number 3. It's pretty similar to the examples 4 and 5, which are given in your tutorial sheet. But I'm not solving them for you. I'm doing it deliberately so that you will have a chance to check your knowledge, to do it yourself. I'm only preparing you for these questions 4 and 5. So my next example for you looks like this. F of z is equal to 1 divided by z plus 1 times z plus 3. Look at this. Our function looks a little bit more complicated this time. And assignment is the same. Find all expansions, all expansions, expansions in powers of z, luckily. In powers of z at least. So we don't need to make any substitution, any new variable, and so on. But nevertheless, this is definitely something new. You know what exactly is new here? We have two singularity points. Let's write it down. Two singularity points this time. Which one? Z1 is equal to minus 1, and the second singularity point is minus 3. What does that mean? Let's try and plot them. It's really interesting what will happen. So this is our complex plane. This is our first point, minus 1. And this is our second point, minus 3. And our method, our algorithm says that plot the circles going through this singularity point. So as a result, we'll get two circles this time. Things are definitely getting more complicated. And what did these two circles do to our plane? They split it into three regions this time. The first region is here, of course, inside the smaller circle. The second region is between the circle. And finally, the exterior of the biggest circle is the third circle. So it means that this time we are going to expect even three expansions. Pretty grim, but what can you do? What can you do? You are given pretty similar task, either question 4 or 5, I don't remember, your tutorial sheet. So you should know how to solve this problem. But you know what? Before plunging into, discussion about how these different expansions should be built, we need to simplify our function. We need to prepare it for expansion. So it can be quite a long story, actually. So let me copy my function here. And so our function doesn't look very good now, because it does not look similar to any of the canonical expansions. That's a problem. And we need to transform it to the form which would remind us at least a little bit some of these canonical expansions. And you know what? We need to maybe this section is actually very familiar to you. When you studied integration, I'm absolutely sure that you came across this example. You were asked at one point to integrate this expression. And to be able to do that, you were supposed to expand this fraction into the sum of two elementary fractions like this. I'm writing it down for you, and probably you will immediately remember. Aha. So these guys are called like elementary fractions or simple fraction, or maybe there are some other names. So the only thing which we need to do, we need to find these constants, a and b. How it can be done? You need to simplify this expression by multiplying this guy by z plus 3 by this denominator, and this guy gets multiplied by this plus 1 uh, by this expression. So let me rewrite it. A times z plus 3 plus b times z plus 1 divided by the same denominator, z plus 1 and z plus 3. And so how can we find our unknowns a and b? So you should look at the very beginning, at the initial fraction, and you should compare it with the final result. Don't look at these intermediate expressions at all. So what can you see about these two fractions? Their denominators are the same, right? That is why you should write the equality of nominators. Initial nominator was 1, and the final denominator is this expression. They should be equal to each other. So this is the equation from which we are going to calculate our a and b. How exactly should be done? There is a very nice trick actually. So this we are not interested in z. This equality should be correct for any z. And that is why we can just substitute any z which we like. For example, I like z is equal to number 3. You know why? Because if you substitute z is equal to number minus 3, this term will be 0. It means that the whole first term will disappear, and we will end up having very simple equation. Let's just do it. So this whole term is 0, and this term will be minus 3 plus 1 is minus 2. Look at this, very nice equation. We can immediately find b from this equation. So very nice trick. And so next time, so we were able to find a b in quite a beautiful, easy way. So it's easy to understand that the next good value of z is minus 1, because minus 1 turns this term into 0. And we will have a very nice equation, a different one, but very nice as well. So let's write what it look like. If you substitute z is equal to 1 here, minus 1 plus 3 will be 2. And this guy will disappear completely. So this is whole equation. And from this equation, we can easily calculate a. A is equal to 1 over 2. So, as you can see, we can write our function finally. So we decided to rewrite our function in this form. But now we know these letters a and b. So let's write down our beautiful result. So our fraction, our function, f of z is equal to this expression. It used to be equal to this expression, but we managed to rewrite it in a more manageable way. Let's say plus 1. This is the first fraction, and the next fraction is this one. So we wrote our function. And now you immediately recognize both of these terms. They look pretty similar to the same canonical expansion which we already used twice before today. Okay, so now it's time to go over the regions one by one. So let's start with the first region, with the interior of the smallest circle. The smallest circle has radius 1. That is why this region could be written as inequality. The absolute value of z is less than 1. Okay, what do we have in this region? What do we have? You know what? Maybe it's a good idea to rewrite this canonical expansion actually somewhere here maybe. So our canonical function looks like this. 1 minus z plus z squared minus z cubed plus so on. And it's allowed to use it only when absolute value of z is less than 1. It's better to have it in hand, or rather on screen. Okay, so what about our function? We need to expand both of these terms, you know. We can expand this term minus and then expand this term. So our Laurent series will be quite big this time. Okay, so here we have 1 over 2, of course, no problem. But what about the remaining expression, 1 divided by z plus 1? Luckily, this looks just like this canonical expansion, and it's allowed inside this region. It's allowed to use it because the modulus z is less than 1. So all we need to do, we need just copy this guys from here, minus z cubed plus so on, and I'm closing the parentheses. Let's move to the next guy. The next guy is not so easy. You know that we need to obtain 1 first in denominator. To this end, we need to pull out 3. 3 plus 1 plus z divided by 3. In this case, maybe it's not correct. I don't know. Z divided by 3. No, it's correct. I was looking at this term and I was trying to decide if I can substitute it here instead of z instead of z. But it turns out that I can, because we are in the region where z is less than 1. So our nominator is less than 1. It means that the whole fraction will be less than 1 over 3. But it's of course it's less than 1. Less than 1. So it is allowed. So now we can do our substitution. So I'm rewriting, copying the first result here, and so on. And here I have minus 1 over 6, 6. And finally, I can use this, I can exploit this canonical expansion. But the only difference is that instead of z, I'm going to substitute z over 3 everywhere. So 1 minus z over 3 plus z over 3 squared minus z over 3 cubed, and plus so on and so on and so on. And as you can see, you know what? Actually, I'm not going to simplify this expansion this time. I'm getting a little bit lazy and tired, and you know how to do it already. Let's just discuss it. This time you can see that we have quite a long Laurent series, but nevertheless you cannot see any negative powers here. It means that again we don't have this principal part of the Laurent series. I'm just discussing it just out of curiosity. We don't actually need to concentrate on this principal part today on this tutorial. I'm just preparing you for the next tutorial, because in the next tutorial it will be super important to be able to analyze this principal part of Laurent series. Okay, now we need to move to the second region, which is between the circles. It actually could be called a ring. So ring can be written as absolute power of z between 1 and 3, between radiuses 1 and 3. And so what do we have in this region? Let me copy our function here again. It's sliding out of screen. So our function looks like this. Z plus 1 minus 1 over 2 divided by z plus 3. Look at this. In the first case, for the first term, we are not allowed to use this standard canonical expansion anymore, because we are in the region where z is bigger than 1. That is why we definitely need to do something to the first term, namely we need to pull out z. So I'm putting out 1 over 2 in front, just for the convenience, and also I'm pulling out z out of this expression, and I have 1 plus 1 divided by z this time. I'll do it a little bit bigger, quicker than in the previous examples, because you're supposed to get used to it already. Okay, so I prepared the first term, for canonical expression. And as for the second term, I think that if we do the same thing, like in the previous example, if we pull out 3, we will still be able to do our canonical expansion. You know what? Let's write it down and analyze it. You know why? Because we will have the same guy, z over 3, but our region is still z less than 3. That is why this fraction will be less than 1. So what is our conclusion? We needed to simplify, to transform the first term in a different way compared to the previous region. But as for the second term, second fraction, we transform it in the similar way, because it's still useful. And so after that, you keep this guy 1 divided by 2 z outside, and now we are using this canonical expansion, but instead of z we are going to substitute 1 divided by z everywhere. So 1 minus 1 divided by z plus 1 over z squared minus 1 over z cubed plus so on. So I'm finished with the first term. Now maybe it's a good idea to highlight this first term, otherwise you might get confused. Too much writing everywhere. Okay, and the second term had 1 over 6 in front. And again, I'm going this use the same canonic expansion, but instead of z, I'm going to substitute z over 3. 1 minus z over 3 plus z over 3 squared minus z over 3 cubed and plus so on, so on, and so on. And maybe I will use some, I don't know, green color. So this is the second term, and this is the second term again. Again, just to save time, I'm not going to simplify this for you. You already know how to do it. I demonstrated it for you on the previous examples. Now I'm just going over more, important things. Okay, so that's how Laurent series looks in the ring between two circles. And you know what? This time it looks like a real full Laurent expansion, because you have negative powers here. This is definitely a principal part of Laurent series. And you also have positive powers as well. So this is like a traditional part of Laurent series. Okay, now it's time to finish this problem, this question, because we still have the last region, the very last region of expansion, which is external region with respect to the biggest circle. So it could be written as absolute value of z is bigger than 3, the radius of the biggest circle. Okay, we need to prepare our function as usually. So let me copy the function first here. F of z is equal 1 over 2 divided by z plus 1 minus 1 divided by 2 z plus 3. And this time we realize that we need to pull out z in both of these cases to prepare our fractions, for using canonical expression. So we already did it with the first fraction, so I can do it a little bit quicker than usual. So from this expression, I'm going to pull out z. And as a result, this expression will look like 1 plus 1 divided by z. That's exactly what we did in the previous, in case 2. You remember? I pulled out 1 divided by z. But as for the second fraction, apart from our 1 over 2, of course, this time I'll have to pull out not 3, but z instead. So it will be 1 over z in front. And the fraction will look like 1 plus 3 divided by z. So only in this case, it will be possible to use canonical expansion in this area, in this region. Okay, so the yellow one will correspond to the first term, and the green one will correspond to the second term. I'm doing this not to get confused because there's too much writing on the screen for you probably. Okay, what about the first term, the yellow one? Well, we use the same canonical expansion. Where is it? I already lost it. Oh, no, it's here. So I'm using the same canonical expansion, but instead of maybe I can feed them both into one screen. Instead of z, I'm going to substitute 1 over z. That's it. So 1 minus 1 over z plus 1 over z squared minus 1 over z cubed, and that's enough, plus so on. Okay, so this was our yellow first term, first fraction. Let's move to the second. I'm moving to the second line, actually. This time, we are going to use the same canonic expansion, of course, but instead of z, I'm going to use 3 over z. Okay, 1 minus 3 over z plus 3 over z squared minus 3 over z cubed and plus so on. So this corresponds to the second term. So that's it. We have finished this task. So it was very interesting example actually, because you can see that sometimes it's not as simple, it's not a short task at all. Sometimes it's quite time consuming, it requires a lot of effort and so on. But you know what? When I looked at your tutorial sheet, I realized that even these 3 examples are not enough for you to be able to solve all these problems, sub-problems from questions 2 and 3. So that is why we desperately need one more example. F of z, 1 divided by 1 plus z squared. And you know what? This time my assignment will sound a little bit differently, because if you read for tutorial 11 carefully, maybe you already noticed that sometimes assignment doesn't sound quite like I said before. All my previous three assignments sounded quite similarly. All the time I ask you find all the expansions, find all the expansions. But sometimes they don't ask you to find all the expansions. They ask you to do something like this: the expansion, find the expansion of this function about z is equal to 0. Look at this. I mentioned you this phrase in the very beginning of this tutorial, but we still haven't had a chance to use it so far. And now it's time. It means that, what does it mean? What do they mean by this expansion about z is equal to 0? Very interesting one. You know what? Let's just discuss this term once again. We already done three examples, but somehow we forgot to discuss. Not that I forgot, I did it deliberately actually, not to distract you too much. Let's just have a look, for example, at our very first example. It's still here. So in this example, we had two expansions, judging by this picture. One was inside the circle, and another one was outside the circle. We didn't give these expansions any names. We just described them by these inequalities. And maybe I used the word like interior of the circle, exterior of the circle. But can this term about some point can be used, applied to this situation? Yeah, the answer is yes. It turns out that this circle actually contains 0. Z is equal to 0. 0 is at the origin of this. And that is why this expansion can also be called about Z is equal to 0. So this expansion, which is inside, which encircles, or how to say, which contains this z is equal to 0, could be called as an expansion of our function about z is equal to 0. By the way, out of curiosity, this expansion can be called about z is equal to infinity, by the way. I've never seen this term in your tutorial sheet, but just for educational purposes, I think it's interesting to know that if you're inside the circle containing z is equal to 0, it means that this is expansion about z is equal to 0. But if you're outside the circle, if you're interested in this area, it could be called as expansion about z is equal to infinity, because infinity is somewhere there, very, very far from in the external area of the circle. Okay, so that is why it means that we need, maybe we could theoretically we could actually do several expansions, or maybe two expansions, but we are asked to write down only one. But you know what, we can start off by our usual tradition. We usually write the point of singularity, which is z minus 1 in our case. We plot it on our complex plane. Let's do it. Z is equal to 1 minus 1 here. And we usually plot the circle going through this singularity point. And the center should be in the center of coordinates, of course. And what can we see? We see that, as usual, we have two expansions. But they are not interested in this external expansion. They ask us to give the answer only for this region. So we are not obliged to do the whole task, actually, only this expansion. That's it. Okay, so this was the first interesting, observation. So read the assignment carefully. Don't do too much, of course, especially during test or exam time, when every second counts. Write the assignment carefully, and after that you might feel happier, much happier, realizing that, oh no, I don't need to do the whole task. I need to find only this expansion. Okay, that's nice. But you know what? Another difficulty, another reason why I decided to give you this task wasn't actually about discussion of this term. It was about this square root. You know what? Of course, it does look like our canonical expansion, but not quite. Canonical expansion doesn't contain this square. It's just 1 divided by 1 plus z. What do you do with the square? You can't square the whole series. It contains infinite number of terms. That is why it's absolutely impossible. There should be another way. The another way is to use another expansion, which was maybe number 3, I think. Let me copy it here. So in the list of our canonical expansion, there was expansion number 3, which was like I like a generalization of the previous of this formula. So if you have a 1 plus z in the power of n, there was a formula which didn't look very nice, but what can you do? N 1 plus 1 nz plus n times n minus 1 factorial divided by 2 factorial, sorry, z squared plus n minus 1 n minus 2 divided by 3 factorial z cubed plus so on. And the region of convergence was the same, by the way. Z is less than 1. Modulus z is less than 1. So that's what we had in our list of canonical expressions at the very beginning of this video. Okay, so in our case, it's pretty obvious that our power n is minus 2. You can rewrite this function as our function f of z. Let's rewrite as 1 plus z in the power of minus 2. So all we need to do, we need to use this canonical expression. And luckily, we are inside this circle. They told us quite explicitly that they are interested only in the area inside the circle. And that is why that's exactly the area where you are allowed to use this expansion, because it coincides with this area. The inequality which describe this inner region of the circle just given just by this equality. So we don't need to do any other simplification, transformation of this function. We are ready to use this formula. And so let's substitute minus 2 n with minus 2. 1 minus 2z, and here I need to do things more carefully. Minus 2 minus 2 minus 1 divided by 2 factorial z squared. And here I prefer to write even more carefully. Minus 2 minus 2 minus 1 minus 2 minus 2 divided by 3 factorial, and I run out of room for z squared plus so on. Okay, let's try and simplify it. 1 minus 2z, and here we have minus 2 minus 3. It will be plus, I don't know, plus 6. 6 divided, is it 6? Yeah, plus 6 divided by 2 factorial z squared. And here we have these two guys will give us 6 times minus 4. It will be minus 24, if I'm not mistaken. 3 factorial z cubed and so on. So, and I'm not going to simplify this expression any further. I am quite happy with it. Let's leave it like this. So the purpose of this example 4 was to discuss this different way of assignment about when you are given explicit region, don't do the whole task, don't do all the expansions. It's quite time consuming and they are not interested. They don't ask you about this. And the second thing was more important. You should realize that there are some other functions as well, because we were too obsessed with the same canonical expansion, which was number 1 or number 2, and we haven't discussed other ones. So this guy looks much different to the previous one. Okay, and the ultimate purpose of giving you this example was actually to prepare you for your question. I should find it now. I lost it in my notes. Yeah. Actually, I was going to prepare you for your question 3, because I'm not going to go over the whole question. My intention was only to prepare you for question 3 from your tutorial sheet. I don't remember which is A or B or whatever. Okay, so in this question, you are given this function, z divided by z minus 1 squared. You can see the square. That was the reason why I decided to give you the previous example 4, to prepare you for this square. And also, in this assignment, they ask you to write 2 expansions. O was about z is equal to 0, and B about z is equal to 1. So it's quite a long task, actually. It's really quite a long task. But luckily, at least they don't ask you to do, all expansions in both cases. But nevertheless, it's 2 different tasks, And moreover, you need to prepare your function first, to be able to start doing sub questions A and B. So I decided to give you some hints. I'm not going to go over the whole problem. I'm only giving you hints. First of all, how to prepare your function. So your function looks like a very fancy fraction, and we need to present it like a sum of easier fractions. So this sum should go like this: a divided by z plus b divided by z minus 1 plus c divided by z minus 1 squared. That's how it should look like. And next, how to find A, B, and C. That was discussed in example 3 today. So I think you should be able to do it by yourself. Please try to do it. It's going to be your like homework, little homework. I can give you answers, by the way. A should be equal to 1, B is equal to minus 1, and C is equal to 1. So let's try to do it by your own head. It's going to be very, very useful for you. Okay, so it means that, so pause this video and try to do these simplifications and make sure that you should be able to find these coefficients very easily. But now I can rewrite my function using this information. So as you can see, this time we have even 3 fractions. Not 2 like in example 3, but even 3 fractions. But it's not so scary actually. Okay, so let's start doing our first assignment, which was to find expansion. But I remember their words. Did they say all expansions about z? I don't know. About z is equal to 0 means only one expansion. I'm almost contradicting myself. So looking at this function, you can look at this form or this form. You realize that you actually have 2 singularity points. Okay, singularity points, 2 of them. So z1 is equal to 0 and z2 is equal to 1 because it's not allowed to divide by 0, even here in complex number theory. Let's plot these points and see how it looks like. We never come across this situation before because our singularity point coincides with origin of the coordinate system. And the second point is 1. But as usual, we need to draw this, plot the circles going through these regions. And as a result, it looks like we have a region, only 2 regions, 1 and 2. But you know, the difference is that this time the center of the circle doesn't belong to the first region at all. So the first region can be written as absolute value of z less than 1, of course, but bigger than 0 as well, because 0 should be excluded. So in this case, mathematicians prefer to say that we are not dealing with the interior of the circle, we are dealing with the ring, actually, because this equality, because it is a ring, because it's the center is excluded. And so, how should you treat these how to say these fractions in this region? Let me just start this problem for you. So, unfortunately, I can't see the function. Okay, I can do it this way. So it turns out that you don't need to do anything to the first term. This was the most interesting thing here, because it's already one of the terms in our expansion. As for this guy, you should prepare it for using canonical expression by pulling out minus here, plus 1 divided by minus that. In this case, this term looks exactly like expansion, a canonical expansion number 2 in our list. Please look at your list. And as for this expansion, we already know how it looks like. We already prepared it in the previous example. So after that, you should be ready to do expansion. So you are not doing anything to the first term, and you apply canonical expansion to the number 2 to the second term. Let me use this highlighting because so this term corresponds to this expansion, right? You don't do anything to this term, nothing at all. Exponential. And finally, as for the second term, we can copy our result from the previous example number 3, but I already lost it. I don't know where I put this paper. It's funny, but I don't know where I put it. Okay, so you can do it yourself. I remember only vaguely that the first term was 1, then it was minus 2z, and then maybe it was 6 or something. I don't remember. Maybe it's for the better that I don't remember. you can finish this task easily by yourself. So this is part A of our problem. What about part B? You are asked to do expansion about z is equal to 1. How this task should be approached? You know the trick. You need to take this z minus 1 and it denoted by t. Denoted by t. In this case, the whole function gets rewritten in terms of t. And to be able to do it, we need to express z. Z is equal to t plus 1. Let's rewrite this whole function. So instead of z, I substitute in 1 plus t minus 1, plus 1 divided z minus 1. It will be minus 1 divided by t, sorry. And this guy will be 1 divided by t squared. This looks even more interesting. Look at this. So what does it mean about z is, again, we need to discuss these singularity points. And this drawing will be made for not for z but what for t. I'm writing for here, t. So how many singularity points you have? 2 again. So one singularity point is t is equal to 0, and the second one is t is equal to minus 1. As usual, we plot these circles. We have interior of the circle, exterior of the circle, but they told us quite explicitly, please give us expansion about z is equal to 1. How can it be rephrased? About z is equal to 1 correspond to about t is equal to 0. About t is equal to 0. What is this region? Again, it's only the interior of this circle. Oh, it's not quite circle. It's not quite circle anymore. Interior of the circle. It's rather a ring, but it doesn't matter. So it means that we are interested only in one expansion, only inside this area, and we need to check as we are going to. We need to write this area correctly. How can we write it? So t modulus t is less than 1, radius of this circle, and bigger than 0, of course. And we need to check that our t is less than 1, because that's when you are allowed to use a canonical expression. Again, we are lucky. So when it comes to the first fraction here, it just looks like canonical fraction, and moreover, it's allowed to expand it here. So let me let me uh, uh, let me expand the first fraction. So all I need to do, I just need to copy this canonical expansion. 1 minus t plus t squared minus t cubed plus so on. So that's my color coding. So the first fraction is expanded like this. But what can I do with the remaining two fractions? The answer is nothing. They are already just, terms of your Laurent series. That's it. So this red guy remains unchanged. It's impossible to expand it because it's already one of the term of this function. And I've run out of colors. I still have green. And so this guy remains the same. And that's it. And don't forget to get back to Z. Wherever you see, wherever you see t at this expansion, you should rewrite it as z minus 1. Don't forget about this substitution. So it turns out that I've done this task myself. You can practice your skills again just by trying to solve this task by yourself. But you know what? I think that you have like 2 or 3 more problems in your tutorial sheet, so you can practice your skill. So that's it for today. That's it.